Okay, I think it has initiated the recording. Yes. Right. So I'm again recording in the cloud, but now I'm doing that in the directly in the tablet because last time it worked there. So let's see. I guess you can still see me, right? I will also use I will use the sound of the tablet so that it keeps my my image. So on the settings, I will leave audio for just a minute. Okay, now I think you can see me. It's just that the audio. No, sorry, I will do the opposite. Right. Okay, so now I will share the screen. Sorry, guys, for this last minute, but there was a problem here at home, and I could not. I simply could not travel in time to Braga. I live in still in next to Vila do Conde, so and I had to. It was not possible to do that basically. Right. So. Okay, so this is just right here. So okay, good. So this is going to be lecture 7, and this is actually the one of the most important ones that you are going to attend now. We are going to talk about several interesting things. And by the way, please keep on the active participation. Don't hesitate in asking questions only because it's online. At least I have that that feeling that people online tend to ask less things that when it's online. So please don't hesitate in asking and stopping me as if we were as normal in the lecture room. So this is so. Right. Okay. So first, where were we in the previous lecture? So one of the things that that if you recall we were talking about, it was about we started with a potential that I will write down here again. So a potential v phi star, and this potential is given by a quadratic term mu squared phi star phi plus 1/4 lambda phi star phi squared. And if our field, if our phi is expanded as 1/√2 phi 1 plus I phi 2, we have verified that in a certain configuration of the minimum, and I will very briefly put here also this in a smaller size, but we'll put it here. So okay, it can be slightly bigger still. So if we have this type of solution here with lambda bigger than 0 and mu squared smaller than 0, we get a symmetry breakdown in this valley of, I would say, equivalent minima. And in fact, we discussed that the symmetry is broken here because we have radial oscillations and angular oscillations that the first cost energy, like climbing the walls of the potential, and the latter that don't. And because of that, this reflects in a mass spectrum where we have something that we call H, because now we're talking about physical fields, mh squared equal to 1/2 lambda v squared, and something G, which is a Goldstone boson. We already introduced that, whose mass is 0. Also, just recall that v squared is equal to phi squared, phi 1 squared, phi 1 squared plus phi 2 squared. This is what we have verified. And also, um, what else I wanted to say, to recall? There was a remnant symmetry here. We wrote down. In fact, I will bring it back from the previous lecture. We wrote down the potential, which is here in the screen. Now you can see it. And there is like a remnant Z2 symmetry on this G field. So this G field transforms into a remnant Z2, resulting from the breaking of U1 down to Z2. This Z2, we found out this Z2 by inspecting the Lagrangian in the minimum of this potential. So we will start exactly by analyzing this guy here, the Goldstone. Why is this emerging? Is this a generic feature? Is it not? So under which circumstances we have Goldstone bosons? So, and for that we will study the Goldstone theorem. There is a theorem saying that these particles always exist whenever you have a continuous broken symmetry. So Goldstone theorem. Right. So what is Goldstone's theorem stating? So it says that whenever this color is not very good, I guess. Whenever a continuous symmetry group continuous symmetry group, let's call G, continuous symmetry group of the scalar potential. So of V, in this case, let's go V in general, because it can V of, in fact, phi 1, phi n, it can have n fields, is broken. Is broken, and this is the key here, is broken to a smaller group, basically, to a smaller group H that is contained inside G. So basically the generators of the H group are part of G. The final scalar potential, so then the final scalar potential, or the final scalar potential will contain contain, and let me in fact write the final scalar potential as a function v of h1 hm g1 gn, let's say. In fact, I'll put m here, I'll put kappa on h. So this is the final scalar potential. Will contain, so the final scalar, will contain one massless particle, one massless scalar for each symmetry generator that is broken. For each symmetry generator that is broken. And each symmetry generator, I will denote the symmetry generators as like TA. So these are the symmetry generators. A equal, it's the A is basically the size of H. So essentially, what happens is that if G, so if G, the group G, has n generators like TA with A with 1 to n, then if H has m smaller than n and preserved generators and broken generators, sorry, n minus m, of course with m smaller than m, with n bigger than m, okay. As n, then if as n minus m unbroken generators, there will be m Goldstone bosons. So as I said, the number of Goldstone bosons is here. So there will be one massless scalar, which is a Goldstone boson, for each symmetry generator TA that is broken. So if H contains n minus m, it means that m was the number of broken generators of the G symmetry. So there will be m Goldstone bosons. Of course, on the contrary, here kappa, this kappa that is here, kappa is equal to m minus n. Kappa equal to n minus m, and is the number of physical Higgs bosons, physical scalars or Higgs bosons with the mass, that have a mass. So this is why in the standard model there is only one. We will see that. We will see that later. Let's see each thing at its time. But now let's demonstrate this this theorem. So demonstration. So now let's consider that first a few considerations about the complex representations. So it's a mathematical theorem, which I'm not sure if there is really a name for this theorem, but saying that any complex representation can always be transformed in a real one, basically in a real one, by doubling the dimension of the corresponding vector space. This is quite intuitive, by doubling the dimension of the corresponding vector space. So essentially, this is you have just realized in the previous exercise. I mean, not exercise. Sorry, in the example of the previous lecture, that if you have this scalar, which is given by 1 over square root 2 phi 1 plus I phi 2. So basically, you can come from a field space which is given by phi down to a field space that is phi 1 phi 2. This is essentially what is meant by doubling the field space. And of course, if you have kappa, so phi 1 and so on, phi kappa, it can be done in terms of real fields like phi 1, phi 2, and so on, phi to kappa, basically. And this is, we can denote this, we can write this in terms of a vector representation, phi. We can just denote this as phi, which is real and transforms under ON. So this is essentially, there is a mathematical theorem that says that all these things are true. So we can write our Lagrangian. So in terms of real fields to demonstrate the Goldstone theorem. And let's do this in general, considering like say this phi. Let's consider this phi as a generic one containing many real degrees of freedom. Basically n or 2 kappa, if you prefer, degrees of freedom. So the Lagrangian is trivially written in this way: 1 over d mu, 1 over d mu phi, so this is a real field, minus v phi. And this is invariant under G and also ON, basically, this Lagrangian. Under G, also ON, instead of this result that we were discussing. So this means that we have n generators. So G has n generators, the symmetry generators. So TA, with A equal 1 basically to n. It's like in a SU2, so we have 3 Pauli matrices, so it's 1, 2, and 3. In SU3, you have the 8 Gell-Mann matrices, so it's n equal to n to 8, and so on. SU4 you have 15, SU5 you have 24, and so on. Right, and now the transformation properties of the field can be right. So the infinitesimal transformation. So small transformations. It can be written as delta phi equal to I omega A TA phi. This is analogous to it's pretty much the same things that we were studying in a U1. So in the U1 scenario, we had I Q alpha phi. So this is what we had essentially. So basically, these omegas are the analog to these Qs, or to this. So these omegas are arbitrary. These are parameters of the transformation. Sorry, in fact, omegas are related with alpha, and Qs, like the charges, are related to the generators, sort of. So this we can write the transformation in this way. Right, and now from the invariance, so we know that V phi is invariant under G. So let's write it here. So V phi is invariant under this G group, and therefore we know that when we do a variation on the potential, it remains the same. So when we do essentially what we are saying is that when we do V phi equals to basically V phi prime. This is what is meant by invariance, of course. So we can write that 0 is equal to delta V. So delta V is this. Sorry, this is not delta V. This is so delta V is V minus V phi, of course. And delta V, we can write this in terms of derivatives. So it's going to be dV d phi I. So we have several phi's, d phi I for arbitrary I. And this is equal. Now we can use the infinitesimal transformation of the fields. I dV d phi I omega A T A I J phi J. Right. So this is the this is from the invariance. This is the result. So as I said, omega are arbitrary. So since omega are arbitrary, we obtain, so basically we can eliminate it, we obtain n equations, which are, so let's write down these n equations, essentially dv d phi I T A I J phi j equal to 0, where we have a equal, and here are the n equations, 1 to n. Right? Is it clear so far? I will I will assume so if nobody.
Sorry, it just
Yes.
something with the indices doesn't seem right.
What doesn't seem right? So you have
Because the I index should be on top on Tij.
okay, that's the summation sort of thing.
Yeah.
But hang on, because the phi I v is a function of the phi I, and I'm putting phi i's on top.
Yeah. And on the upper line, for example, you had phi I contracting with delta phi I,
Yes.
and that makes sense because the I on top at the bottom of the fraction makes it like an I on the bottom, and so it contracts. But
Let me just okay, so we solve this in a, we can just put summation here, because here I'm putting the i's, I can put all the i's not on top but below, in fact. um, and I just wanted to avoid the summation, but yeah, I see what you mean. But then the notation will become slightly
I guess, yeah, the T would have to have the I on top, so it would be like
the I
TA
and
and then
even the J
IJ,
in
and
that
it would
case.
be awkward.
But
Yeah.
I can put the i's below. Well, but hang on. So because when we are taking um, the phi I, just give me a second here. This is easy to solve in another way, which is if you do this, sum in I.
Yeah.
Is, and here it will be sum in I and J, if you want to be more precise in that. Sum in I and J, we can do this. And also here below. But now I will have to remove all these lines and right here. I mean I and J. So I can sort of drop the summation. Sorry. Now it is just that when we are doing this, you want to so the notation typically is even with the a's, both a's on top. I just don't like to abuse from this notation, but people rarely put sums here and use the
Yeah.
indices, like say repeated indices are being summed. And what I'm telling you is that from here onwards we are going to do the same sort of thing. So repeated indices
Okay. Yeah.
are going to be summed. Here I write the summation just to make this concrete. But now I will write, and now that things are clear here on the screen, I will write that, and also because I'm saying that V is a function of this. In fact, above here, I put the indices below. I guess no, I didn't specify. I said it was phi 1, phi 2, phi 2k, but now I'm using big phi, so I'm saying this is V of phi 1, phi 2. Well, this is not explicitly putting the indices on top. This is just an identification. The index J runs over of this, so I could put it either on top or below, which actually doesn't make a difference. So I can actually put the I here. This I could put below. It doesn't make a difference. But let's just use like this and say we are now. Let's now drop the sums. So basically all repeated indices are summing. So let's take this from here onwards. So still, the important part here is that we get so I will rewrite them. So we get n equations. So n equations are this d phi. Let me put the phi here below. Tij a phi j equal to 0. These are the n equations. And now we can differentiate this. Let's differentiate these equations. And what do we get? So we will have d2v d phi I d phi k t I j a phi j plus dv d phi I t a I j d phi j d phi k equal to 0. And so you know this one here is delta jk. Now with the indices in the as Osvaldo likes. So this is equivalent to having the following. In fact, d2v d phi I d phi k d I j I a phi j plus dv d phi I t I k equal to 0. Now let's go to the minimum. So basically what happens in the minimum? So what do you think will happen? I'm writing, but you can reply. So this is evaluated at the minimum. I will write here the phi I equal to v I t I j I phi j plus dv d phi I phi I equal to vi. So this is in the minimum. So in fact, this is, we would say this is a verb here, vacuum expectation value t a I k. This is equal to 0. Yeah, but what's happening here, guys? Can you tell me what is this? Anybody? So nobody wants to answer. Don't you remember what is this? When we are in the minimum, so we are in an extremum. what happens to the first derivatives?
0.
Yes, finally. As simple as that. So this is going to be 0. And what is this? What is this here? Again, someone to reply. The second derivatives. So we found, what was this? This is like the key point of the demonstration.
Laria just said in chat that it's positive.
Exactly. So right, but physically, what's the meaning of the second derivatives? What we take from the second
Well,
derivative?
it's the mass matrix.
Yes, yes, exactly. So this is indeed what we get. So here, this will turn out to be then. It's not writing. It's writing now. M squared. This is the squared mass matrix. So we put a square there. Ik. This is the mass matrix. T Ij A Vj equal to 0. So this is what we obtain from here. And now let's we will come back to this, but now let's just look what happens to the infinitesimal transformation. So we have these infinitesimal transformations, delta phi. Let me recall this: delta phi equal to I omega A T A phi, right? And if the action, so let's consider and now consider a generic orthogonal matrix. Let's call it Q, acting on the vacuum V, basically. In this case, it's VI on the vacuum VI. And you can, you know that you can write to first order. So Qij, so you have this matrix acting on the vacuum Vj, and you can write this as an expansion in terms of this this group. Basically, there is an identity part. This is something that we'll talk a bit more in this SM2 course, in in the introduction to group theory. And then there is this part where we have this infinitesimal shift. So it's the same group. So we have this this structure: I omega A T A Ij Vj, and this in general is not equal to Vi. So basically, this is just to say you can write a generic Q, so any matrix Q, using the identity and the generators of the symmetry. This is, and we discussed that also when we looked into the Clifford algebra. We said that with the gamma matrices and those combinations of gamma matrices, we could write generic 4x4 matrices. And this is precisely the same thing. Well, not in terms of gamma matrices, but in terms of the generators of a different symmetry. This is different than I, if, of course, if this is different, if basically T I J A V J is not 0. So this is to say that for at least one generator, a certain A, Ij, Vj is not zero, then the symmetry is spontaneously broken. Okay. As the vacuum is no longer preserved. Is no longer preserved. So saying that the vacuum is no longer preserved is this condition here holding, essentially. So you act this matrix on the vacuum and you get something different. So this is to say the vacuum is not preserved. But this is not always the case. The vacuum may be preserved for some generators. So if we now consider H, this H that is a subgroup of G, and is considered H a remnant symmetry in the vacuum VA or VI. So this is, for example, in the previous scenario, we had the U1 going down to Z2 that we just discussed above. We noticed the potential had a Z2 symmetry in the G, in the Goldstone bosons itself at this G symmetry. So we can say the vacuum has that, the potential has that symmetry. That would be Z2 would be the H and U1 would be G. So this is what we have discussed. So consider H a remnant symmetry in the vacuum VI, such that H contains M less than N generators. So we have M generators. So for the unbroken generators, or the preserved ones, for the preserved / unbroken generators, the ones that those of H, basically the ones that will generate the H symmetry, the condition Qij Vj equal to Vi must hold. So basically, these are the generators that preserve the vacuum. So see here above again. So if this is zero, so this is zero, this guy goes away, and then this preserves the vacuum. Essentially, you only have the identity part, and you act the generic matrix on the vacuum, and the vacuum is preserved. So this is what we mean by preserving the vacuum. And the generators where this happens are those where there is a remnant symmetry. So therefore, so this implies that T A I J Vj, as I was saying, equal to 0. So this gives us the unbroken generators. So it's the example, for example, in the standard model itself, we have the electroweak symmetry, and in the vacuum, we have the electromagnetism. There is one preserved generator. Out of 4 initial generators, there is at the end 1 preserved generator. So we are left with 2 possibilities here. So these are left. A. As we said, TA, IJ, VJ equal to 0, and nothing can be concluded about the mass matrix M squared IK, because let's go here and see. So this is the condition that we are now going to recover. Let me pick this up again. And put it here. Right? So if this is 0 already, it doesn't matter what is in this mass matrix, right? So there is nothing to say. In the case of the preserved symmetries, there is nothing to say. But if we look to the broken generators, and this will end the demonstration of Goldstone theorem, if Tija Vj is non-zero, and we have this that we have here above, this green thing, then M squared IK has a 0 eigenvalue for each of the generators that break the symmetry or the vacuum, or break the symmetry in the vacuum. And this is the point. These 0 eigenvalues for each of the generators that break the symmetry. So these are going to be these are the Goldstone bosons. And this has a profound impact because the emergence of these Goldstone bosons, and this ends the demonstration, by the way. So the presence of these Goldstone bosons is crucial for the emergence of mass in gauge bosons. This is the other result that we'll discuss today as well. So this is quite an important result, and is the Goldstone theorem that I have demonstrated here. Of course, you could be a little bit picky and say now we should also demonstrate that that these 0 eigenvalues indeed correspond to eigenvectors. Yeah, that would be like a fully complete demonstration. I will not go into those details. In most of the cases in the literature, this is considered enough, and we are assuming these are indeed the eigenvalues of the mass matrix. But here and there, you see some demonstrations that have this also try to prove that the eigenvalues do correspond to eigenvectors. Just to say, because the boson itself, it's an eigenvector of the theory, basically. So it is now instructive to relook into our Goldstone. So recall that we had our potential previously written in terms of H and G, which is here, this H and G potential that I'm now showing on the screen. So we had this, but we know that we have these massless states, and this confirms our findings. But we also know, we have also verified, and we can still look in previous lecture, also today's we have that the Goldstone bosons correspond to these angular directions in the field space. So there is a more exact way of parameterizing our field instead of the linear description of the field. Instead of writing it as phi equal to 1 over square root 2 the vacuum V plus H plus G X, so this was HX as well, HX GX. Instead of writing like this, we can explicitly put the Goldstone bosons in a phase and write it as phi equal to 1 over square root 2 V plus HX. Of course, the phi's are also a function of X. Only for a moment I will keep the X's. So these H's H's and G's are quantum fluctuations. And then we can put this in an exponential form here. E to the I. And let's now call theta, because it's not exactly the same as, let's for a moment call it theta. This is an exact formulation, let's say. And to first order, you can expand this to first order in theta. We have, so phi x is approximately 1 over square root 2 V plus hx plus theta x, I theta x. This is easy to check, but this theta, the theta and the G are not exactly the same. Here we are writing things in two different ways, but both ways are equivalent. In terms of physics, both ways of writing are equivalent indeed. And to show you, so that with this, when you do this, if you write your scalar in terms of putting your Goldstone boson, and I want to put also an X here. If you put your Goldstone boson in this exponential, so this is the non-linear formulation of your field. So you do a non-linear definition for the fields, so the scalar fields. This drops out from the potential already. So the V becomes a function only of H, and is given by, so 1 over 16 lambda, this is a lambda H to the fourth, plus 1 over 4 lambda V H to the power of 3, plus 1 over 4 lambda v squared h squared. So this is the mass term minus like a vacuum energy term, 1 over 16 lambda v to the 4. So here we have the mass. So this is the mass. And then we have quartic and cubic interactions, or here in the, so this is a triple interaction here, and this is a quartic interaction of this Higgs boson. But bear in mind that theta is still a physical field. We are talking about a global symmetry. In this problem, in this example, we have U1 global. So recall this, we have a U1 global. So the Goldstone boson is not, is a physical field. It's not absorbed by the gauge bosons, as we'll see how it happens. So it also must have propagating degrees of freedom. So it drops out of the potential, and I think you understand why, right? Guys, everyone is understanding. Does it? I see something in the chat. Okay, positive. It was hilarious saying something. Sorry if it's too late. But yes, I think we're talking about n. Right. So please, guys, are you understanding why G is dropping out of the potential? From who's not understanding? So everybody understands.
I didn't get it.
Okay, good. So please, guys, you should ask when you don't get, because this is very important. So G this case theta, I'm recasting the Goldstones in terms of theta. So there is first of all a correspondence here between, well, it's not a correspondence, but it's a different way of writing the fields, which is equivalent. Why is theta being dropped out of the potential? I will very, very, very easily tell you, and you will immediately understand. Because our potential was, so our potential v phi star phi is equal to mu square phi star phi plus 1 over 4 lambda phi star phi squared. Is it now clear? So basically, this is phi. You have phi and phi star always in your potential. So the phases go away, right?
Right. Okay. Yes.
And then you just expand this in terms of your vacuum field. So you use this expansion that is here in the red box, and only H is the radial oscillations around the minimum are left. There is no more Goldstone in the potential. But this is not the full story, because the Goldstones, they are still there. They are still propagating degrees of freedom, and we need to take them into account. So we know that we have the Lagrangian, that is, and I will write for concreteness, d phi star d phi minus v phi star phi. This is our potential. We still have the kinetic terms. So let's consider the kinetic terms. So essentially, what's happening is that we have d mu phi star d mu phi, and we can expand this in the nonlinear formulation. So in terms of this field written in terms of the exponentials. So basically, now I'm going to take the derivatives of this field. And what we get is the modulus, so because these are complex numbers, of d mu h e to the I theta over v plus v plus h I over v. So I'm taking the derivative of of d mu phi, d mu theta e to the I theta over h modulus squared. Modulus squared because this is indeed what is here. This is modulus d mu phi squared. So with this, the exponentials will just drop, but theta is here. So theta is here in this place. So this becomes, we can rewrite this as 1 over 2 modulus. I will already write in terms of components. So we have dh squared plus d theta squared v plus h squared over v. This is just taking the squares. And if you expand this, this is going to be 1 over 2 dh squared plus d theta squared plus 1 over v d theta squared h plus 1 over 2v squared d theta squared h squared. And here just note that I mean by so d theta squared is simply d mu theta, should be theta, d mu theta, d mu theta, and dh squared is the same. So d mu h, d mu h. So just for completeness. So the first thing is that you see that there are propagating degrees of freedom. So there is a kinetic energy term for theta. This is what makes them physical. They are propagating degrees of freedom. So they are in the theory. So this is predicting a theory which has also a physical h. So there is a propagating degree of freedom, which is h, but has a mass. But our theory also has these propagating degrees of freedom. And furthermore, these they have interactions with each other. So they have cubic interactions here, and here quartic interactions. And these interactions, so let's do only for the cubic, and then you can do yourself maybe as an exercise for the quartic ones. I will formulate the last exercise sheet of these parts. So for this d theta squared, what do we have? So let's look. Let's look to the cubic term, to the cubic term. Cubic is in terms of fields. Let's look onto the theta squared h. So first of all, we know that if we do d mu theta, d mu theta h, this is 0 because this is a surface term. So this is only, I'm starting from this point. This is not what is in the expansion above. So this is just recalling this is a surface term. That's why this is 0. So so we can say that 0 is equal to d mu theta, d mu theta, d mu theta h plus theta. And now we have here d mu theta h plus theta d mu theta d mu h. And this one here in the middle can be written as theta. This is the Lambertian operator, theta h. And you know that the Klein-Gordon equation for so the Klein-Gordon, so the equations of motion, in fact, for theta is theta equals 0. This is the equations of motion for theta, basically, because it doesn't have a mass. So m theta equal to 0, m theta squared equals to 0. So this term drops, and we can write that d mu theta h equal to minus theta d mu theta d mu h. So also observe that this first term here, this first part here, can be further recast because this is equal to. So let's just recall that if we have d mu theta squared, this is equal to 2 theta d mu theta. So we want to further rearrange this to get to our final. Basically what we want to do is to remove all derivatives from here. We want to look only into interactions without derivatives. So we are trying to remove them, essentially. So this means that theta d mu theta is equal to 1/2. This is trivial. D mu theta squared. So above here, I will just write minus 1/2 d mu theta squared d mu h. But we can again use a surface term using the trick of the surface term. So use again so as we are using surface term only to rearrange these derivatives. So our d mu, so we can say that d mu theta squared d mu h. So this is 0. So it happens that d mu theta squared d mu h plus theta squared, and again a Klein-Gordon equation for h, or I mean the D'Alembertian operator h equal to 0. But now we know that this here this bit here is no longer 0 because H has a mass. So this is equal to minus mh squared H, because the Klein-Gordon equation, or the equations of motion, are like plus mh squared H equal to 0. This is where we are taking this from our Klein-Gordon equation. Therefore, we say we can write that d mu theta squared d mu H is equal to theta squared. So we have a minus sign coming from the mass. Theta squared, I will actually write in a better organized. So mh squared, theta squared, H squared. So we have this, H only. Therefore, we can we come here again. So let me put here a star. So there we have that d mu theta H is equal, which is what we denote by d theta squared H is equal to minus 1 over 2 mh squared theta squared H. And for the quartic, I'm not going to do for the quartic. Similarly, for the quartic interaction, we get that d theta squared H squared is equal to minus mh squared theta squared H squared. So finally, we get from our kinetic terms d mu phi conjugated d mu phi. This is going to be equal to, now we are going to write in terms of the real components, in the Higgs and the Goldstone boson. It's a d theta squared plus a dh squared. This was written above. And now we are just going to rewrite the other two interactions, but removing any derivatives. So we will have mh squared over 2v theta squared H minus mh squared over 2v squared theta squared H squared. So these are the new we will recast this triple and these quartic interactions in terms of physical degrees of freedom. So here one of the key points is that the Goldstones the Goldstone boson theta is a physical slash propagating, because it has kinetic terms, degree of freedom having interactions and kinetic terms. This is a problem when we have Golson bosons, in fact, because these are highly constrained, if not completely excluded. So when we have a global symmetry that is spontaneously broken, we ought to do something about it. And typically what we do is we add an explicit breaking term to prevent the theory from having Goldstone bosons. So here just to make things concrete, so you have noticed that we have our Goldstone boson, which is massless and has interactions and propagating degrees of freedom. So this is the kinetic term for the Goldstone boson. This is the kinetic term for the Higgs boson. This here is the cubic interactions involving a power of 2 Goldstone boson and 1 Higgs boson, and this is a quartic interaction with 2 Goldstones and one Higgs boson. Note that these interactions, the coefficients in front of them have the right dimensions. So this is a cubic interaction. So scalars, they have dimension 1. So this thing inside this circle has dimension 3, and this coefficient has mass squared over v, which has mass dimension 1. So this together has dimension mass 4. And here it's the same. So here it's dimension 4 already. So the mh squared has the same dimensions as the v squared, so the things cancel out, and so everything is fine here in terms of dimensions. There are other interactions as well that we have written above, which are the interactions coming from the potential that involve only Higgs bosons. So this would be all interactions in this theory, in this pathological theory, I would say, because we have massless Goldstone bosons that we don't want. So to remove them, there is typically a trick or something that we add to the potential to remove them. We want to remove the existence of Goldstone bosons explicitly. So the degree of freedom is there, but we want to make it massive. But we know that this doesn't work if we do it spontaneously. Of course, the most elegant is localizing the symmetry, making it a gauge symmetry. But there is another way out. Sometimes we may have accidental symmetries, and those are not local. And if they are continuous, we need to consider the possibility of explicit symmetry breaking. So, one possibility. Yes, please ask.
Sorry, just about these Goldstone terms,
Yes.
the cubic and quadratic terms. I was just wondering if we can just interpret them in a way as some kind of perturbations, because it looks like because we're subtracting these terms, and I was wondering if this could be like small in some limits and be ignored or something like that.
Well, this is one of the things is that this both h and the theta, they are always quantum fluctuations. So these are all we prefer a regime where they are small. Of course, that's of course an important point. And but yes, indeed, theta. In fact, we can make an expansion for higher orders of theta, and this only works, of course, in the limit of small theta. That's
Okay, I see.
that's
Thanks.
true. That's well observed. So typically, what happens is that when we have this but still the oscillations. So this is an angular field, let's say, and we are considering we can rotate our axis such that theta is more or less around 0. So it's just rotating around oscillating around 0. So this is a small field. But by definition, these are quantum fluctuations even in H. So these are field excitations, and they are preferably they are small. So, but still they are physical. They are still physical. So that's the
Okay.
thing. So they exist, and if they exist, they could be excited. and they could be seen. And we have not seen Goldstones, and they would be very easily seen. They would possibly contribute to dark energy, dark matter. So it could be, they could have some nasty consequences. So dark radiation, essentially, that we don't see, basically. Okay, so one of the possible ways of removing the Goldstones is by adding an explicit symmetry breaking terms. So let me write here. Explicit symmetry breaking. This is a lot simpler than spontaneous, but less elegant. Let's say it's something that we force by hand. So this is a possibility. So it's a possibility in order to give mass to global Goldstone bosons. Global because we are talking about continuous global symmetries. So that's why I want to point out clearly this global here. This global is important. It's not a local. A local Golson boson is in fact a gauge boson, as we will see. So what to do? So we have our V phi star phi that can be turned into a new potential. So we have the V phi star phi, and we will add a mass term that explicitly breaks U1. The problem is the U1 symmetry. So let me even point out that here. So the problem between these quotation marks, the problem is the U1. So this is the one symmetry, or any continuous global symmetry in general. So this is not a problem of only U1, it's for any continuous global symmetry. In fact, U1 is the less problematic one, because if you have larger symmetries, you will have more Goldstone bosons, so the problem will be bigger. So the problem grows with the size of the continuous symmetry that you add to your theory. So this is let's add a term that violates this U1 symmetry by adding a square term plus its complex conjugated. Squared, and let me put here square brackets to be neater. So this is the explicitly breaking term. Explicitly breaks U1. And I guess that you, if you remember the field transformations, so we had phi going to phi prime equal to phi e to the power of minus e q alpha, as well as phi star going to phi prime star equal to phi prime e to the I q alpha. So these were the transformation properties. Now, what happens is that because of this, the phi square term, goes to phi squared e to the minus 2 I alpha, which is not the same as phi squared. And similarly, the other term, phi squared conjugated, goes to phi conjugated square e to the 2I alpha, which is not phi conjugated square. So this means this is why exactly. So the Lagrangian is no longer invariant under U1. Let me put U1 here to save space. U1. So of course, this typically these terms are called soft breaking terms because they are not typically they are not very big. These are typically small contributions. And their purpose is indeed to give mass to Goldstone bosons. There's also a type of explicit breaking that is done in supersymmetry. So because of the lack of supersymmetry at not the non-observation, but yeah, it has to do with the fact of us not having ever observed supersymmetry. That is telling that supersymmetry is not exact in nature. And needs to be broken, but nobody, or it's very hard to spontaneously break supersymmetry. And typically what people do is adding soft SUSY breaking terms, like these explicitly breaking terms, but not for a gauge symmetry, for a space-time symmetry, in that case supersymmetry. Also note that this potential, there is another symmetry that if I only put this to phi squared and phi square star terms, I could put more. I could put a linear term, like something like I could put something like phi plus phi to the power of 3, only up to the up to the order 3, of course, plus complex conjugation of this. But I decided to not put these ones, just to call your attention to a symmetry that emerges here, which is the following. So we have with mu1 terms, the new model contains and I'd say a Z2 times Z2 symmetry. What are these Z2s? So basically, in one of them, we see that we have phi goes to minus phi conjugated, and another Z2. So this is, we can call this Z2A and Z2B. So Z2A is this transformation, and Z2B is this transformation. Phi goes to phi conjugated. So these are two independent transformations in the potential, and in fact, so let's look into the operators that we have to make sure that this is indeed the case. So in the case of the first, so we have phi squared goes to minus phi conjugated squared, and this is trivially phi conjugated squared. So this, what's happening here is that you are transforming this term into this one here. Right, so let me write mu here. So our mu is, so our mu1 square term is equal to, there is any combinatorial factor I didn't put, but that doesn't matter. No, phi squared plus phi conjugated squared. So basically here we transform phi squared into phi conjugated squared. And this is the first Z. Let's make here a column just to identify. Then the second I will write in red. The other is we have phi. Sorry, this is still the green one. It's the transformation of the other field. So phi conjugated squared, this goes to minus phi conjugated. So we just have to transform phi to minus phi conjugated square, which is equal to phi squared. So the other transforms this into that, basically. The second is easier. The second is easier. Simply, we have phi squared goes to phi conjugated squared, so it's immediate, and phi conjugated squared goes to, it's trivial to see, phi conjugated square, which is phi squared. So this proves that the Lagrangian has these two symmetries, and of course the bilinear term of the other part, the U1 part of the potential is still invariant under these Z2s. So this one is also invariant because it's a modulus, so it's phi star phi. It's always transforming into the other. Right. So what does it mean in terms of mass matrices? So with this, we have the new stationarity condition. So when we had this this new term.
Sorry, just a second.
Yes, as well.
No, I just got told that Alexandra is trying to connect and she's not being able to.
Okay, I will. Let me see. It's not here. I don't see. Maybe can you ask her to try to connect again?
Yeah, just give me a second.
I'll just write down here. View new. U1 preserving part, and this is at least, are you contacting her as well?
So she's saying she's getting the message that the meeting host needs to let her in.
Maybe it's here in my tablet. Hang on.
Oh yeah.
Because I am the host.
Yeah, the tablet is the host.
But I'm not seeing any. There is some activity here. This is on. This was what Ilaria said. Oh, I don't find here any. So where the hell should I? No. Participants, maybe here. I'm not used to do this in the tablet.
She just showed up.
Okay.
Yeah, just wait a second. I think she's the second I told her to try to reconnect, her name showed up there. So I think she shows up in the participants. Yeah, so right
Here,
there.
okay. Now I can admit, yes.
Okay,
Okay,
everything's fixed.
Okay, Alexandra. I hope you didn't lose a lot. So I was saying that we have a new potential that is made of a U1 preserving part and a U1 breaking part, and this is the U1 explicitly breaking part. So we need to recompute the stationarity conditions for this full potential. And what we get, it's now we get more conditions because of this Z2 cross Z2 symmetry. This potential has a Z2 cross Z2 symmetry. So there are actually 5 possibilities for the stationarity. I will just write here what are the stationarity conditions. Stationarity conditions, or the stationarity points, in fact, stationarity points. This is what's going to be written here. So first, a phi1 0 or and phi2 equal to plus or minus. So these are 2 possibilities here already. Plus or minus square root of 4 mu1 squared minus 2 mu squared over square root of lambda. There is another one where phi1 equal to phi2 equal to 0. So the A is already 2 of them. It counts already with 2 possibilities. And C, finally, the last 2 possibilities, it's just reversing, basically rotating from phi1 to phi2. Phi1 equal to plus or minus. Well, it's not exactly that. It's there is still here some signs. So we have minus 4 mu1 squared minus 2 mu squared square root lambda, and phi2 equal to 0. Right. So what happens in the when you look into the graph of this? So first of all, let's look to the mass matrices. I will just write with condition A. So with condition B, it's the same as you've seen before. It's a symmetric potential, as we have seen before. But with condition A, the mass matrix becomes M squared becomes 4, and this is already, in fact, this is already should be small m. This is already like in the minimum. So this is already the physical mass matrix. 0 and 4 mu1 squared minus 2 mu squared, and B and C, and for the scenario C, m squared is equal to, this is after diagonalizing already. I'm not doing the full thing here, but this is after diagonalizing. 4 mu1 mu1 squared. So we are already in the physical basis. Mu squared, 0, 0, and minus 4 mu1 squared. So, right. So this here, what do we see? If one of the conditions that we have here, for example, is for mu1 squared to be positive. So this this should be a squared here, mu1 squared. So here, mu1 squared is positive, and also this here is positive. Of course, here I'm also considering that I'm also considering exactly 0 2 mu1 squared. So 2 mu1 squared is between 0 and minus mu squared, where we have mu squared is negative. So bear in mind the sign. So this minus mu squared is positive. So this thing here is positive because mu squared is negative. So here we are in a minimum. We're in a minimum and we have no Goldstone boson. No Goldstone boson. But if mu1 is small, the size of mu1 is much smaller than much smaller than mu, than the size of mu. I mean the modulus. Then we denote this. Then we have m. We can call, let's call theta, m theta squared equal to 4 mu1 squared is, okay, and this is not as a pseudo, so pseudo Goldstone. I don't know if you heard about it, but this is the definition of a pseudo Goldstone. You give a tiny mass by this breaking mechanism, by this explicit breaking mechanism. On the other case, C, we have this first one is still bigger than 0, but minus this one is going to be negative. So this is a saddle point and not a physical minimum. So this C is a saddle point here. With these conditions, C is a saddle point and this is a minimum. And now can we visualize this just before having a break? Let's visualize this here. Let me put in the other here. So you can see here that we have the minimum here, and on the other side as well, there's the minimum on the other side. There is a saddle point here, and a saddle point also somewhere hidden there. And of course, we have here our local maximum. But you see the two minima here, you come here to this condition A, and there was like, it was phi1 equal to 0 and phi2 plus or minus this value. And this is what we have. So we have a Z2. So in this direction, we have like a Z2. We do a Z2 identification, and we go back to the other minimum. And it's the same here for the saddle points. So we have a Z2 Z2 transformation, and we put the field on the other side. But we no longer have a valley. You see, there is no longer this valley of degenerate minimum. There are only two minima here, this green point and the other one on the other side of the potential that is not visible here. And you can no longer, to repeat the potential, you need to rotate by pi radians. Not any rotation will give the same thing. So to get to the same point, you need to do this pi rotation. So this is why the symmetry, the Z2 symmetry, is discrete. It's not continuous. You don't. It's not like in the U1, in the full U1 scenario where we have a continuous. You can do a continuous rotate, and your potential is always the same. Here, it's not. You do a rotation, and the picture changes. Of course, you can say that if this, so this deviation from the Mexican hat case, the Mexican hat case is this is this previous one. That let me put use the one from the previous lecture. It's the best option. So this is the Mexican hat case here. If mu is very small, there is only a tiny deviation from this, and this it would be such a tiny deviation if we zoom in. Of course, with the growing mu1 parameter, so with the growing of the size of the explicit symmetry breaking, this becomes more pronounced, and we are further and further away from a U1 symmetric scenario. But this is what happens when we have explicit symmetry breaking. So you get some these shapes in the potential, basically destroying the phase invariance as we had in a full U1 theory. Okay, so let's have a small break, guys. Can it be 5 minutes so that we can make good use of the rest? So just for you to have a quick rest, and myself as well, and then we continue in 5 minutes, slightly before 12. Okay.
Yeah. Okay.
Good. So any questions anyway in the meantime? Okay.
Excuse me.
Yes.
Sorry, I'm really sorry. Can I ask a question about the homework, or you prefer it I ask at the end of the lecture? I don't know.
Maybe at the end of the lecture.
Okay, sure.
Because it can take some more or something. So at the end of the
Yeah,
lecture, we talk a little bit. Okay.
Okay, great. Thank you.
Very good, very good. So 5 minutes, guys. I will just pause the recording. Okay. Are you guys all there? Sorry for this this cough, but I had some hazelnuts that created this. Let's see if this one cleans this up.
More will fix it.
Yeah, exactly. There's a little bit of pill that was stuck.
Yeah, yeah, yeah.
Sorry. Right. Okay, so I guess you are all here. Okay, so let's change the topic, but in a way extremely related to this one. So I would say let's change for another subtopic, and this will be called the Abelian Higgs Mechanism. So the Abelian Higgs Mechanism. So what is our goal here is basically vector boson mass generation. Mass. We have studied the Higgs potential very carefully with several possibilities at hand, but we have not yet, in fact, understood how to give masses to vector bosons and to fermions. But now let's concentrate first on the vector boson case, because it's the really neat and the most interesting one. It's basically what is the motivation also behind this? It's the fact that we have vector bosons in nature that in principle should obey gauge invariance, but we see mass. So this is telling us, as we have discussed in the beginning, that possibly there is a larger gauge symmetry that is broken in a gauge consistent way. It's broken in a gauge invariant way, let's say. And this is what we are going to study in a simple example. That's why I'm calling the Abelian Higgs mechanism, because the standard model is not Abelian. Standard model is non-Abelian. But this is a lot easier to introduce the concepts if we study the Abelian Higgs mechanism. So let's first recall the transformations. Now we are going to a U1. So Abelian Higgs mechanism means, so Abelian means here U1 local or gauge symmetry. Or gauge symmetry. Right. So what are the field transformations? Let's just recall them. So we had a phi going into phi prime, and phi prime equal to phi e to the minus I, a certain charge, q alpha x. Now alpha depends on x, and phi star goes to phi prime star equal to phi star. So now I am constantly showing this. So you should have this. I don't know how to say in English. Ponta da língua. You need to know this by heart from here onwards, basically. So the Lagrangian now also, because a local symmetry implies that the derivatives become the covariant derivatives. as we have studied last week or 2 weeks ago. So the Lagrangian now, the same Lagrangian, but now with a U1 local symmetry, a gauge symmetry, it's given by d mu phi conjugated d mu phi minus v phi v star phi. And there is something else, because now we have a gauge field, so minus 1 over 4 f mu nu f mu nu. So this is our theory now. The new ingredients are the gauge covariant derivatives and the field strength tensors. The invariant, the Lorentz invariant product of the two field strength tensors. So we already know a few things. The potential is exactly the same. So this is exactly the same. So this means that we have already know that we have a Higgs boson mass, which reads 1/2 lambda v squared. But we have a Goldstone mass, which is 0, of course. And we also know that there is a minimization condition that was making this mu squared equal to 1 over 4 lambda v squared. So you remember this mu was the mass term in the potential, the quadratic term in the potential. So the potential, let me write here small, so was mu squared phi dagger phi plus 1 over 4 lambda phi conjugated phi squared. So this is the potential. So by minimization, this is by minimization, we obtain this. Well, in fact, all of this. Minimization and rotation to the physical basis. To the physical basis. We achieve this, right? So now the important piece to start looking to is are these covariant derivatives. I'm going to partially expand the covariant derivatives. So let's do that. So we have this d mu phi conjugated d mu phi, and this is equal, just remember that, so in fact is 1/2, we can write this as 1/2, and now modulus squared of d mu plus iq a mu, which is the covariant derivative, acting on so the field expansion v. So we are starting not with the exponential form, but with the linear expansion. Gx modulus squared. So use phi equal 1 over square root 2 v plus h plus ig. So we are using this at the moment. And upon expansion, let me write only the important points. So we have 1/2 dh squared. So this is a kinetic term for for H, for the Higgs boson, plus 1/2 dg squared. So once again, we have a kinetic term for the Goldstone boson. So they appear to be physical. So far, they are looking physical. Plus 1/2, and now there is something interesting happening here. Q squared v squared a mu. So this term resembles a mass term for gauge bosons. It has the form of a mass term for gauge bosons. Plus, now we have something which is Q d mu g a. So in fact, let me write this in a QV a mu. And this term is troubling. Of course, we have more. We have higher orders, so terms with the higher orders on the fields. Terms with higher field powers, higher powers on the fields. In fact, only up to order 4. So 3 power 3 and 4. So I guess you understand what is meant here. So what we have here, once again, we have a kinetic term. You have a kinetic term for the Goldstones. We have something that has the structure of a mass term to gauge bosons. So this is already going in the direction that we want. So is this a mass term, ma squared? Question mark. But we have an offending term here. This one here. Let me call this is an offending term. Because this term, what is happening in this term? So I write in orange, so you can see the orange. Yes, you can. So G and a mu can transform one into each other, into another. Thus, we cannot interpret, or you cannot promptly interpret the a mu term as a mass for the gauge field because what's happening here is that we are transforming two fields, one into another, G into a mu via this orange term, which is telling us we are not in a physical basis. Or something, or if we are in a physical basis, something is not yet fixed here. And we need to do something about it. And now we are going to cure this, or to understand what's going on. We are going to write again the field. So phi x phi x
Sorry,
inside. Yes.
why do you say that you're transforming one into another? I didn't get it.
Okay, okay, right. So here in this term, this is a bilinear term, right? So what happening here in this orange is that you have you can write a propagation of for these ones here. Like you have a Feynman diagram, something like you have a G here, and then there is a mass or an insertion here which is proportional to QV, and you get your mu. So if your
Okay,
time, you see what's going on, what's happening. So if you're reading your time like this, and this can be the opposite, it can go in the other direction as well. So you can transform your G into an A and vice versa. You can write then all possible interactions on both ends here, but you can transform one into another. This is what is meant here.
Okay,
Is it
thanks.
clearer now with this diagram?
Yes.
So that's what's happening. So for example, a mass term, so the gauge boson mass term that is here, it's simply if it's a pure mass term, it's something like that. You can say, okay, there is a mass insertion here in the middle, which we write q squared u squared, but we have a mu in one side and a mu in the other side. So we are not transforming the field here. No, there is like a non-diagonal interaction. I mean, bilinear interaction via this mass insertion. So this is what happens when you have bilinear terms. It's you are transforming one into another, and you don't want a mass term or in the mass basis, in the physical basis, to transform something into something else. If it's a decay, it's fine, or if it's a cubic quartic interaction, it's okay. Those are interactions.
Hi, sorry again. Mark was having issues getting into the class as well.
Okay, thank you, Oswald. So why the hell don't I see? I don't see that because I'm using the screen. That's the thing. Sorry, it's not here. It's here.
Check the participants list.
Yes, exactly. It's here.
Okay, I mean, he's not there. Or maybe he just, because it said 9 just a second ago.
Ah, okay. He said it was quite a long ago. It was at 12:05.
Yes,
Let
8
me reply
minutes ago.
because he sent me an email.
Oh, he's there. He's there.
Okay. Marco? Marco, are you with us? You may be muted, so just to confirm that you can
Ok,
hear
já
us.
consegui entrar, professor.
Okay, so did you
Espero
lose a
ter
lot?
perdido muito. Ok.
I can quickly scan over what we discussed.
Ok.
So we started with the Abelian Higgs mechanism. I don't know if you heard it already. So we said that there is, and actually for the rest of you, it's also good for you to cement this. So now we are going to basically convert the U1 symmetry that was global into a local one, so a gauge symmetry essentially. And the transformation laws are given by this that we have seen before. So now alpha is a parameter that depends on the position, on x, basically. We have to put derivatives, transform it into covariant derivatives for the reasons that we have studied before. And we need to rewrite the Lagrangian as it is here on the screen now. So the Lagrangian, we need to put covariant derivatives in the kinetic terms. The potential is exactly the same, no difference. And we have to add this, the field strength tensor. So basically the Maxwell, the Lagrangian, we have to add it here. And because the potential is exactly the same, the minimization conditions are the same. Everything is the same in the scalar potential part. So we know that this model has a Higgs boson, one Higgs boson, one Goldstone boson with zero mass, and this is just the minimization condition to replace mu in the potential. And now if we do expansion with the field phi, that is written here, in terms of h, so this is the linear formulation in terms of h for the Higgs, the quantum fluctuations in the radial direction, and g, the quantum fluctuations in the angular direction, we achieve by expanding the kinetic terms, which is here. This is the kinetic terms. We reach a point where we have of course, a nice quadratic term for the Higgs, which we need. Sorry, a kinetic term for the Higgs boson. So it has kinetic energy. It's a physical particle. We also have one for the Goldstones. In this case, it's only one Goldstone. We have something that resembles a mass term for gauge bosons. Here, it's a quadratic term in a mu, and the mass would be this, q squared v squared. But I'm putting here a question mark. Is it really a mass? We need to understand if it is really a mass or not, because we have here an offending term where we have a g and an mu, which means that there can be a conversion of, so basically g can be transformed into a mu and a mu into g via this bilinear interaction with this insertion here. If it was only the mass, it's fine, because the particle transforms into itself, and this is what the mass is supposed to do, but not transforming one field into another one. So we need to do something to solve this problem. Try to see if this is indeed a mass term or not, or if we are in the best gauge for it to happen. Right, Marco? Did you get the idea so far?
Yes, I can work out the details later.
Okay, you can work out those details. So right, now, to see what happens, let's expand the field in terms of of the nonlinear formulation, as we have seen in the previous hour. So we do here v plus hx and exponential I, and now I'm going to write here gx over v. I'm writing g because it's more intuitive for Goldstone, but as we have discussed before, this is the theta that we used in the previous for the global case. So this is not the same g as the one in the linear formulation here. It's not exactly the same g, but it will have the same interactions. So it's no harm to call the same naming here. So here we are already putting the Goldstone as a phase. So this is Goldstone as a phase. Okay, because we know we have a Mexican hat potential, and it can go around. So this phase can in the E1 phase rotations, let's say. Now the transformation on the phi, and now I will drop the x. Phi transforms as, I will write it again, phi e to the minus I q alpha x, right? And a mu, we also seen that a mu transforms, oops, so a mu transforms as a, it goes to a mu plus d mu alpha x, the exact same alpha x, and we have here we have a gauge freedom we have gauge freedom to choose alpha x. So what we want to do is basically fixing the gauge. So let's fix a better gauge. Let's fix our gauge to, And this is, of course, it's based on inspection of the potential. This is to go in the line of our purposes. If we choose alpha x to be equal to gx over qv, we have the freedom to do this. Gauge invariance is still there. So this is our gauge choice. In fact, let me write this is instead of, because there is gauge fixing is similar to this, but it's in a different context. So let's choose, and here I will just write gauge choice. This is our gauge choice. This is our gauge choice. And this means that now with this choice, we have phi is equal to 1 over square root 2 v plus h e to the I g x. So this is actually what we have above, but this goes to now the transformation. The transformation phi goes to, it's here above, phi goes to the minus iq, this minus iq alpha x. So let's rewrite this with the, and you understand why this choice of why this choice basically of the gauge choice, the choice of gauge choice. This is equal to 1 over square root 2 v plus h e to the I gx over v and e to the minus I q. So this is the basically the gauge transformation part, qv. So this is the minus iq alpha. So just to make things concrete, this is our alpha x here. And of course, you see the exponentials just cancel out because the q's cancel, meaning that we have phi prime our phi prime is equal to 1 over square root 2. Well, this is a bit strange way of writing. 1 over square root 2 v plus h. So this is our phi prime. Now, because we are choosing the gauge, we should start writing what are the primed fields. And similarly, our a mu prime is going to be equal to a mu plus 1 over qv d mu gx. So typically you have d mu alpha x, and now alpha is gx over qv. So we have here alpha is gx over qv. And this is our gauge field. So now we are going to replace these two in the Lagrangian, taking into account that we know because of gauge invariance, we do have that L phi mu is equal to L phi prime mu prime. We know this. So let's once again expand the kinetic terms in the primed for the primed fields. So we get that d mu phi prime d mu, this is mu phi prime conjugated d mu phi prime, and we can now use, it's a lot simpler because the phi prime, there is a prime missing here, phi prime now doesn't only has v and h, so this is phi prime here. This gives 1/2 the h squared plus 1/2 q squared, and this h should be yeah, I will keep h. This is the same h. This is the same h. And now we have a mu prime, a prime mu. Sorry, because I only want to write the relevant interaction. This is but this is there, 1 q squared v squared, yes, q squared v squared plus higher order terms, interaction terms. And here now we can clearly interpret this as a mass squared. So this is mass squared, or 1/2 ma squared a mu prime. We no longer have the offending term. We no longer have a term mixing G with A. And you understand why? Because we are using the this we no longer have G in this phi prime. So this drops out from the degrees of freedom here, provided that we use a prime as well. We are using a prime here in the expansion, and saying that okay, the Lagrangians must be the same. So this is what we should see. And in fact, to see that the thing holds, if we expand this term here in terms of the fields, let's put here. So in terms of so 1/2 q squared v squared a mu, this is equal to, as we had before, 1/2 q squared v squared a mu plus 1/2 d mu g. So this is d mu squared, to write it faster, dg squared plus qv, this was the offending term, d mu g a mu. So let me use the same colors I used before. So this is the mass term. This was in the previous potential in the same way as it is here. This was the kinetic term, and this was the offending term. So, but what's the thing here? By a redefinition of a mu, a choice of this gauge, you can remove not only the offending term, you remove the offending term from the theory, but you also remove the kinetic term. You see, the kinetic term is no longer there. So what's happening? You are absorbing G into the definition of A prime. And in fact, there is a quite important consequence of this, or that we are getting mass. It seems that 1 degree of freedom, G, is one of the. Let's analyze once more the degrees of freedom now, just to see what's happening. First of all, do you understand what's happening here in what is in the screen now? You basically remove, by a redefinition of A prime, and of course phi prime, you still have kinetic terms for H, but you remove the kinetic terms of G and you remove this offending term. And now you can clearly interpret this one here as a mass term for your gauge bosons that was absent before the symmetry breaking, but it appears now. So before the breaking, how many scalar degrees of freedom we had? So degrees of freedom. 2 from the scalars, which in fact is H and let's call G. We define this plus 2, which are basically the transverse polarizations of a massless gauge boson. So recall that the gauge boson, the photons, they only have transverse polarization. One is a magnetic, the other one is an electric. You can see in that way, but the longitudinal, there is no longitudinal polarization. Photons only oscillate in the transverse plane to their propagation. And this is for any massless gauge boson, this is the case. Their oscillations are perpendicular to their direction of motion, let's say, to their longitudinal polarization, which it doesn't exist. They don't have polarization in the longitudinal direction. But after the breaking, what are our degrees of freedom? So we have 1, which is only one scalar, H. G is removed. So I will put here with G is removed. So it's no longer there. Plus 3 for the A mu. So here it was the original A mu, and here it's now A mu prime. 3, which are transverse and longitudinal polarizations of massive vector field. So we are not removing degrees of freedom from the theory. We are basically transporting it from the scalar sector to the gauge sector. And with that, we are giving a mass to the gauge bosons. And this is the essence of the Higgs mechanism, essentially. And with this gauge, I will repeat once more, the choice of gauge that we have made here this gauge choice, it's fixed now. This is our gauge choice. We don't go to an arbitrary one. This is our gauge choice now. Alpha is equal to G over Q times V. We remove kinetic terms of the Goldstone boson from the series. So the Goldstone boson is no longer physical. The Goldstone boson as a scalar, as a propagating scalar, is no longer physical. We don't have these offending terms, and we can now interpret this a mu as a mass term to the gauge bosons. And this is you see this immediately by expanding the covariant derivatives with the gauged fixed fields. Let's say phi. Look, phi only has h here. Now, also for the scalars, for the scalar potential, just for completeness, once again, the scalar potential only has so V phi star prime phi prime is only terms in H. So there is no G in the theory any longer. And we say that G was eaten, basically, G was eaten by the gauge bosons. So the formal description of this being eaten is these transformations here. Basically, you see G comes here to the definition of a prime. And this is the formal, let's say, description of saying that the Goldstone boson is eaten by the vector bosons. Of course, from here onwards, we will simply rely on these results, and we will not putting primes on all the fields, and just assuming that we are already in the correct gauge choice. Right. Of course, there are some Feynman diagrams that you can draw in the notes. You can check in the notes. There are some Feynman diagrams in the notes. This is not. I may rephrase things there a bit because it's not very well explained. I reckon it's not explained in the best way. This unitary gauge and how to do this. I may rephrase that in the next days and upload a new version. But you can even find there how to get Feynman diagrams out of the interactions. But essentially, you get interactions with. So if you keep on expanding these kinetic terms, you get, for example, interactions with so gauge bosons, like gauge bosons, right? And scalars. So A, H. This is interaction with Higgs and scalars, and you also get quartic interactions as well, like one gauge boson, another one, and two scalars like this. And also from the scalar potential, you have, as we have discussed before, you get more possibilities. So to finish this module, there is only one thing left, which is not very heavy. We can, I think we still have some time, 15-20 minutes. I hope it's enough for this. But is how to generate mass for the fermions, basically. No. Fermion mass generation. So here we will need to basically to complete the Abelian Higgs mechanism. So it's basically it's the Abelian Higgs mechanism. We are doing this in the context of the Abelian Higgs mechanism. Higgs mechanism with fermions, with chiral fermions. With chiral fermions. I typically call this the Abelian Standard Model. Right, so so for that we need to define what are our fields. Let's talk about scalars and fermions. So we have a scalar, we have a fermion psi and another fermion. So these are chiral fermions, and this is to mimic as much as possible the electric sector in the standard model. That this is the idea behind this. So we have these fields, and we can write down their quantum numbers under yeah, because we are defining a U1 here we are calling B, and a U1C symmetry, both local. There was a homework which is similar to this, but one of these is global. So I'm saying that here phi has charge 1 and 1 on both of these symmetries. Psi, I'm telling you, it's charged on under U1 and neutral under the other U1. And chi is neutral under the first U1 and charged, but with minus under the other U1. So this defines the transformations. With this, you can define the transformation properties. Phi goes to phi, but now we have two transformation parameters. E to the I. Let's write here G alpha. So I'm not putting Q's, I want to put G. This is the gauge coupling. G alpha X plus G prime beta beta X, because we have two U1s, and this is charged with charged 1 under both. But psi only transforms under the first U1, so it's E to the I G alpha X, and chi transforms as chi E to the minus I G prime beta X. So it's only charged under the second one. So it does not have, so this one has the parameter, I will write here, alpha X, and this one beta X. And then we have also G and G prime. So G and G prime are the gauge couplings. G and G prime are the U1 B and U1C gauge couplings. Respectively. And the message that the gauge couplings or their interpretation is that they are introduced in order to distinguish the two U1 transformations, or in other words, they set the strength of each of the the interactions. So basically, the sizes of G and G prime set the strength of the corresponding gauge interactions. So basically, how strong do they interact with the gauge fields? How strong fermions interact with the gauge fields or scalars is given by the size of these G's and G primes. So this is what gives what tells that the strong interaction is strong, the weak interaction is weak, and so on. And if there is a gauge coupling for gravity, if gravity is one day is quantized properly, let's say, and if it's fundamental, then that G would be tiny, very small, because it's the weakest of the known interactions. We also said that there is a B mu. So instead of having A mu as before, we have B mu is the U1B gauge field, and C mu is the U1C gauge field. And the corresponding strength tensors. So instead of F mu nu, we will have B mu nu and C mu nu, basically. Right, so we can write the Lagrangian involving all these interactions. And what we have is, so the Lagrangian is, there is first a line for the scalar sector, which is d mu phi star d mu phi minus v phi star phi. This is a scalar sector. So scalar sector. Then we have a pure gauge sector, or the kinetic terms, the gauge kinetic sector, minus 1 over 4 b mu nu. B mu, this is the Maxwell generalization of Maxwell Lagrangian to these two new interactions, 1 over 4 c mu nu, c mu nu. So this is like the Maxwell Maxwell-like sector. We have kinetic terms for fermions, for the chiral fermions. I, psi bar, gamma mu. And here now we are going to define covariant derivatives. We need also to define the covariant derivatives. D mu psi plus I k bar gamma mu, and this big D, d mu chi. These are kinetic terms for fermions. And finally, we have y psi bar phi chi plus complex conjugation, which is a Yukawa interaction. So all these terms are allowed by the symmetries. Of course, I should define also the covariant derivatives here. But before I define the covariant derivatives, there are three. So one covariant derivative is this. The other covariant derivative, it's with this labeling. And there is a third one, which is this, because the fields have different transformation properties. So I'm defining three different ones. But before writing them, let me just show you that that the fields these terms are indeed invariant. So, for example, here the last term. So the psi bar has charge -1 because psi has charge 1. So psi bar is -1. In terms of we have the U1b, and we have the U1c. So in terms of U1b, psi bar is -1. Phi, phi is also phi is 1 and chi is 0. So this is invariant. So it's just summing the exponentials. So it's a product of the exponentials that's summing the argument of the exponentials. This is what I'm doing here in a shorthand notation, let's say. This is the easiest way of doing it, just summing the charges. For U1c, we had psi bar, psi is 0, phi was -1, and chi 1. So this is also summing up to 0. So this is allowed. Of course, it's here in the potential and in the kinetic terms, because of the conjugation, it's allowed. There is no question. The gauge fields are neutral under this, so it's also no question. And here above, also you have like in the psi bar psi, it's also no question because of the field and the field conjugated. And because of that, you have these terms, the kinetic terms for fermions are also allowed, of course. They are allowed. But note, interestingly, that you don't have mass terms of the form psi bar chi plus complex conjugation, of course, because this term is forbidden. And this is what happens in the standard model, not with two U1s, but with one U1 and another and an SU2. But it's the same story. Because look here, in terms of the U1b charges, psi bar, it's -1, psi is 0, so this does not sum to 0. And for the U1c is the same. So here it's 0 and chi is -1. Sorry, it's 1. So mass terms are forbidden. And the homework that I uploaded last Tuesday goes along these lines. Also, you may convince yourselves that if you expand, so because these are chiral fermions, so psi and chi are chiral fermions. Which means that, and we are using the Weyl basis for Weyl representation for gamma matrices. So if you have, for example, if you define a psi d, a Dirac, which is equal to psi and chi bar, then we are defining, and here let me still use here a notation. So psi d, and here these are two component ones. Let me use the same notation that I gave you, which was, no, I don't remember the notation that I gave you, but this is, I can quickly check that just for concreteness. Yes, I just added here saying these are left Weyl spinors. So these are left while spinors, the ones that are here inside. Left-handed while spinners, while spinner. And the same with the other one. These are both left-handed while spinners. This was one of the previous exercises for you to understand this. So you are writing this as what we are defining our psi is that psi is the left chiral projection of psi d, and chi is the right chiral projection of psi d. So this is and of course, so this is equal to psi L0 in 4 components, and chi is equal to 0 chi bar L. So this is typically even the software packages that are used in to calculate when you build a model and you want to do calculations. You always use this the Weil basis and write Dirac spinners in terms of chiral of 2-component Weil spinners in this way. But Lagrangian is written. This Lagrangian is clearly written in terms of Dirac chiral spinners. Right. So just the covariant derivatives. I'm just saying there is it's already 1. So since this is almost there, but it's still a little bit, I'm asking you, what do you guys prefer? Do you prefer to finish it for good now, which maybe 10-15 minutes more, or use that time in the first next lecture will already be, so next week on Thursday will be Standard Model 2, but we can just finish this up. What do you guys prefer? Do you want to say something?
Well,
I would like to finish if that's
Yeah.
actually, yeah, that's
Okay.
possible.
I
I
prefer
think
to
it's
finish as
best.
well.
Okay. Okay. Good. So let's finish. I just I was feeling uneasy, thinking that you were extremely tired. You may be tired, but we can finish. I also prefer to finish, but if you wanted to go, I would. We would do that next lecture. But okay, let's then do this. So I have explained. So these are chiral fermions. I explained the notation. What is psi? What is chi? This is in your exercises as well. So this is similar to that. This is the Lagrangian. I have built this this Lagrangian that is here now on the screen. I still need to define what are these covariant derivatives and explaining them. And I told you that the mass terms are forbidden, and I think it's clear from here. Of course, because of the notation that we are using, it doesn't make sense to write psi bar psi, because this is simply equal to 0, or chi bar chi. I'm kind of solving part of your exercise already, but this is what why these terms don't make sense in the in this when you write when you're writing this chiral fermions. They don't exist. These ones here, you can check that explicitly. So these are all interactions that we have in our Lagrangian. What are these covariant derivatives? The covariant derivatives is what they depend on the field that they are acting on. So the curly D, the first D's ones here, they are acting on the scalar, and the scalar has, as you can see, has 2 charges of U1b and U1c, and it's like Q equal to 1 here. And because of this, of Q equal to 1, so this curly D, you just make it better. This curly D mu is going to be equal to the normal derivative, and then the first, so Q equals to 1, So we only put the gauge coupling here, I, G, B mu, and from here onwards, we'll start using the gauge couplings. It's a gauge theory, so we need to use gauge couplings. When it's global, G is 0. So, so the global limit is putting G's to 0 pretty much. So there is no interaction. If G is 0, the interaction doesn't exist. Plus I G prime, it's the second, C mu. What is now the second covariant derivative here? This flat d mu. This d mu, so it's acting on psi. So let's come to the table. Psi only has u and b charges. So this will be similar to the ones that you were used to see. So this flat d mu equal to d mu plus I G b mu. And finally, we have this other big D, this capital D, d mu, which is acting on chi. So chi has minus one charge of u and c. So it's the beta. But here we are not using beta, but the G prime. So it's minus 1. So because of that, we are going to write here d mu equal to d mu minus, because of the charge, I G prime C mu. Right. So now we have all ingredients, and now we can expand the potential. And I will only write the relevant terms. So let's expand first the scalar sector to see what happens to the mass. What happens to the vector bosons? We have two gauge bosons. So we have. So what happens to the vector bosons or gauge bosons? Masses. Basically, we have C mu and B mu, B mu and C mu. So, and here you see d mu. So d mu has b mu and c mu here and interacts with phi. So this will give masses to the gauge sector, but how? So d mu phi conjugated d mu phi. This is equal to modulus, once again, so let me just 1/2. To save space, I will just write modulus square here as well. I need some space here. D mu phi modulus squared, of course. So this is equal to 1/2 modulus of d mu. In fact, let me just copy this. This d mu, and now phi, we are using here again the linear. Let's use the linear definition of the field plus Ig. So the Goldstone, there is one Goldstone here. So we only have one Goldstone. So that is interesting. We have two gauge bosons, but we only have one Goldstone. So expanding this gives like 1/2 v squared. No, it's g squared. I will write b squared. This is b mu, plus, I'm dropping the mu's now. G prime squared C squared, which is C mu, plus G prime BC, it's B mu C mu, plus G prime G prime G, C mu B mu. Of course, these things commute, but for the purpose of looking into a mass matrix, this is the most convenient way. Plus, and now I'm going to write this in the color that I used for the offending terms, plus G V dg B plus G prime V dg C. So we have, in fact, here I can write the mu's because it doesn't cost anything. The mu, C mu. Okay. So we also have these offending terms, which means that, of course, here we also need to do the exact same thing as we done before. And if we choose the gauge appropriately, let's choose. If we choose the gauge, so choosing the gauge, now we have two gauge groups basically. So now our choice is such that Gx over V is equal to G alpha x plus G prime beta x. So it's a little bit more involved, but for simplicity, and also using the gauge freedom, this is also part of it. For simplicity and using gauge freedom, set alpha x equal to beta x, just such that we can replace. So our identification now here is alpha x equal to Gx. So this is the Goldstone, G plus G prime V. I'm not going to do the same exercise as above, but what happens now is that with this, we will absorb these offending terms once again. And our gauge kinetic term, sorry, our covariant derivative. Now in terms of primed fields, primes, now we have primes here, B mu prime, C prime, B prime, C prime. Like this, we have our, and we, in fact, let me also remove the Goldstone from here. The Goldstone is no longer here. And this comes here. So this is doing the exact same thing as in the previous exercise. And now we can trust this as mass terms for gauge bosons. For gauge bosons. But they are not diagonal. We still have to diagonalize them. And that can be done. So we have a mass matrix. We can directly read a mass matrix from here. So our mass matrix, M squared equals to V squared. So 1/2 is always dropped out. So the basis is like, we are writing this in the basis, which is BC. So the basis is BC, or B mu C mu if you prefer. So we have G squared, so B here. So you're taking this is taking the second derivative once again with respect to B and C. G squared, then G prime, G prime, G prime, and G prime squared. And now you can define a rotation matrix. Equal to, for example, use this cos theta, or actually the one that I used here, which is equivalent to sine theta. Cos theta, it's familiar to you. Cos theta minus sine theta. Diagonalize m squared and m squared such that this new diagonal m can be done by just doing like OT m squared O equal, and this gives the following: v squared 0, 0, 0, and here it's g squared plus g prime squared. So we only have one massive gauge boson. Only one massive gauge boson. Only this one. In fact, this can be, it's a Z-like boson. And this zero eigenvalue, it's a photon-like. So we have two physical fields, MA, with the first as we all write MA squared equal to 0, and MZ. So we have a photon and a Z boson in this model, whose mass is V squared G squared plus G prime squared. And in fact, note that we only had one.
Professor,
Yes.
I have to disconnect because I have a bus to catch right now.
Okay.
Okay.
Okay. Right. So this will be recorded anyway, and you can.
Okay.
You can see the
So
rest.
until next week.
Okay. See you next week on Thursday. Okay. We are approaching the end, so it's almost. We are almost there. So we have this. This is the photon and the Z boson mass. But recall that we only had one Goldstone boson. And having only one Goldstone boson, you only have one degree of freedom to be absorbed. That's why you remain with the massless field and one that becomes massive. The Z boson here becomes massive because it's the one that is absorbing the G, the Goldstone boson, and not A. A does not absorb, and that's why we have a massless field. And in fact, this translates into saying that our original theory was a U1B cross U1C theory, but we broke down to a remaining U1A. If the standard model was not electroweak, but was this U1 cross U1, this U1A would be the electromagnetism, where we would have a photon, a massless photon. Also, note that using this rotation matrix, this rotation matrix gives you the eigenvectors, pretty much. So you can write your A mu and Z mu, so the eigenvectors. So the massless combination, so A mu is sine theta B mu plus cos theta. And this will be important for the interactions with fermions. And Z mu equal to cos theta. V mu minus sine theta c mu. And you can also redefine in this basis. You can define G, and basically this theta is the analog of the Weinberg angle. This is the analog of the Weinberg. If you heard about the Weinberg angle, this theta is the analog of that in this model. And you can even redefine G's in terms of these angles. And a new thing that we introduced is E, is what we are calling an electric charge. Let's say the unit of electric charge. E over sine theta, and G prime is equal to, this is defined in order to use, I will explain why is this defined in this way. E cos theta. Of course, then you can rewrite the Z boson mass in terms of E and theta, but that's only replacing G and G prime there. And now, what happens to the fermions? So to see what happens to the fermions, we expand. The fermions don't have a mass yet, but we will expand their kinetic. Well, first we know that using this term here, this is the Yukawa interaction. The Yukawa interaction. So let me place it here. So fermion masses here. So we pick up this Yukawa interaction, and now we know that phi is equal to 1 over square root 2 h plus v, or v plus h. So this interaction here will yield the following. So y over square root 2 psi bar h chi. So this is an interaction between the Higgs and the fermions, plus y over square root 2 v psi bar chi. And now this here is a mass term. So this here is m for the fermion. So let's go f. So this is how masses are generated for fermions. Basically, it's via this this interaction with Higgs. So there, the first term is an interaction term. The second is a bilinear, and now it's allowed because the symmetries were broken, and this is a reflection of the broken symmetries. It's now allowed. So psi and chi have a new symmetry, which is this U1, and we can easily find the charges of this U1, and one of the ways is by expanding the kinetic terms, which we have here. Let me grab them. This is the last step, the last thing to do. We pick up these terms here. We grab them. Okay. And let me paste it here. So this is going, if we expand, so we are going to get, let me put this in the previous, in fact, in the previous. So let's get the charges. Let's find the gauge interactions of the fermions in the U1A phase. So basically the theory after the breaking. So I will paste it again here. So we start from this, and we get now, of course, the first it's trivial. I psi bar gamma mu d mu psi plus I chi bar gamma mu d mu chi plus, and now it's where we are also going to use already this definition of the fields. So we need to write b mu and c mu in terms of a mu and z mu. So write b mu and c mu in terms of a mu and z mu. And when you do so, you find things like this: E gamma mu a mu chi bar chi plus E gamma mu a mu psi bar psi minus E and E cot theta gamma mu. So these are currents that we are writing here. These are neither currents. Z mu psi bar psi plus E tangent theta gamma mu Z mu chi bar chi, and of course plus the interactions with the Higgs that we already discussed. And look, here we have this interaction with a field. So this is the interaction with the electromagnetic field. Let's say this is there is an electromagnetic current here, and here you see that the coefficient is the same for both chi and psi. So they have the same charge, the same U1 charge. Otherwise, this interaction would be different. This means that now you can see why is this term allowed here, this term here, because they have the same charge, and it's E. So one is minus E, and the other one is E. And this sums up to 0, and this is now allowed. And likewise, the same in this interaction here in the interaction with the Higgs. I'm not now expanding the kinetic terms of the Higgs, but it's a good exercise for you also. It's also here. It's also preserved. But this is the nice thing. This was forbidden in the beginning. Let's see again. It was clearly forbidden here. There was no way it could work. And now we have spontaneously generated a mass for fermions, and now it works here. And finally, we have here two other interactions. This, I'm just taking the minus as well. We have this interaction, and we have this interaction here, which are pretty much the interactions with, let's call the Z boson, these are the weak currents, let's say. And here it's different. The interaction strength of psi is different than that of chi. So they interact differently with these Z bosons. They have different coefficients. In fact, we can write the Feynman diagrams of these guys. So, for example, for psi, like this, and we have or for exactly chi psi, and then we have sorry, this is the mass term. It's not one that I want to write now. So chi psi and chi bar psi bar. You can think you can think of chi and psi as like left and right fermions in the usual way, as you say in the standard model. This is a mu here, and this is equal to minus E IE gamma mu. This is the Feynman rule. But you also have two different interactions, two other interactions with these z's. One is for psi. This is psi bar, and this is z mu. And z mu with psi comes with a minus sign, so it's minus e. This I is always there. Cot e gamma mu. And finally, you have this chi bar interaction with z mu, which has a different Feynman rule because it's a different interaction, e tangent theta gamma mu. And that's it, essentially. So you see, from the key goal is that from a theory that had where masses for fermions and gauge bosons were forbidden by gauge invariance. So I think it's clear this was forbidden, and the gauge symmetry itself forbids mass for gauge bosons. But now, after an appropriate choice of gauge, and after breaking the symmetry, one of the Goldstones gives mass or is absorbed to provide a mass to one of the gauge bosons that becomes our Z boson. The other one does not absorb any Goldstone, that doesn't exist, and it's massless. It's our photon-like candidate. This breaks the symmetry from U1 cross U1 down to a single U1, and all the mass terms that were forbidden now have become allowed, both for fermions and for vectors and for scalars we had seen before in the previous discussions. Okay, guys, so this ends this module. So today was, sorry for not having there today as I was expecting, but there were some shortcomings here at home and I could not leave. Next week I will already be there in person, and there will be 1/3 exercise, so homework for this, that I will put online as soon as possible. But you can hand in 2 weeks time, not exactly next week, but 2 weeks from now. I would say sometime before Christmas. So any questions? I don't see anyone wanting to ask anything. Not here in the chat. Okay. So
Yeah, so I actually wanted to ask a question about the homework. So
okay,
I don't know.
let's leave. Okay, let's leave everyone else if you want to leave, and you can ask me that, or if someone else wants to ask also something, just wait a bit. So you have that homework question. So the others, anything about immediate, or is it? If nothing, you can just go, and I will discuss with Merave just what's her questions basically. Okay, so guys, let's end this. I will only end the recording because of this. This is the end of the lecture. And see you next week.
Okay, bye-bye.
See you.
Bye-bye. So maybe you can ask your question now.
Yes.
Let
So
me just
actually,
stop the recording. Sorry, just wanna. So I need to do this here. Okay, stop.